Newton's law of gravitation. It is unlikely that Newton really did have an apple fall on his head, but what he did do was realize that the force pulling an apple to the ground is the same as that causing the moon to orbit the Earth. His logic went something like this. If we fire a cannonball from a tower, it will fall to Earth, like this. Fire it faster and from higher, and it will travel further. The Earth's surface is falling away as the ball falls. If we fire it fast enough and from high enough, the ball will fall at the same rate as the Earth's surface falls away from it. The ball is in orbit, just like the moon. Using laws of planetary motion previously worked out by Kepler, which are not required for this course, Newton worked out that the gravitational force of attraction between two bodies was directly proportional to the product of their masses and inversely proportional to their separation squared. We can write that like this, or adding a constant of proportionality like this, where F is the force of attraction between the two bodies, measured in newtons, m1, the mass of object 1 in kilograms, m2, the mass of object 2 in kilograms. R is the distance between the centre of masses of the two bodies, in meters, and G, the universal gravitational constant, which has a value of 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. This is known as Newton's universal law of gravitation. The minus sign is because the force acts in the direction of the vector from mass 1 to mass 2. The force due to gravity is always attractive, and so acts in the opposite direction to this vector. For an object on Earth, the force F is simply the weight, mg. For an object of mass m on the Earth of mass m sub e and radius r sub e, we get this expression. So the weight is simply equal to the attraction due to gravity. I've missed off the minus sign here as I'm just looking for the magnitude. We can cancel for the little m's on either side to give this expression. The gravitational field strength, little g, is equal to the universal gravitational constant given by capital G multiplied by the mass of the Earth divided by the radius of the Earth squared. If the mass of the Earth is around 6 times 10 to 24 kilograms, and the radius of the Earth around 6,400 kilometers, we get this. And this gives a value for the Earth's gravitational field strength of 9.8 newtons per kilogram. Gravitational field strength G is defined as the force per unit mass. The force due to gravity does obey an inverse square law, meaning a doubling of the separation between two bodies will lead to 1/4 of the original force, giving a graph something like this, with force falling off rapidly as separation increases. On Earth, we're already 6,400 kilometers from the centre of mass of the Earth when on the surface. So if we go up by just a few kilometers, we notice no change in the force due to gravity. Here we have a diagram of the Earth with arrows showing the gravitational field. The field lines are further apart as we move away from the Earth. This shows that the gravitational field strength does reduce with distance. If I enlarge the picture like this, the spreading is a little less obvious. Adding more arrows, then expanding the picture again and again, these field lines now are very close to being parallel, showing that for a reasonable distance above the Earth's surface there is little change in the gravitational field strength.